In this video, we will talk about the central limit theorem. Actually, we're not going to say very much about the theorem itself, but we will rather focus on the implications that it has for our purposes. The central limit theorem concerns the distributions of means of samples drawn from the same population. In other words, we're talking about the sampling distributions of means. To illustrate this concept, let us start with a population. This is a large population with normally distributed values with a mean of 0 and a standard deviation of 1. We will draw thousands and thousands of samples with size 10. So 10,000 different samples with size 10, completely randomly drawn. We will then draw 10,000 samples of size 100, and then 10,000 random samples of size 1000. For all of the samples of size 10, we will calculate their means and standard deviations and produce the histogram of means and the histogram of standard deviations. And we will do the same for the samples of size 100 and then for the samples of size 1000. So here is the distribution of means of samples with size 10. As you can see, this is a fairly spread distribution between the values of -1 and 1 and centered around the true value of the population parameter of 0. So these are means that you could have gotten if you sampled with a size of 10 from this population. You could have gotten any of these values. And this is the histogram of standard deviations from these samples of size 10. What about the larger samples? These are the means and standard deviations of samples of size 100. These are the means, and these are the standard deviations. And these are the means and standard deviations for samples of size 1000. Remember, these are histograms of statistics. They're not histograms of your measurements or of the data. They're not histograms of any sample data. They're histograms of means on the top row and histograms of standard deviations on the bottom row. Because in a simulation, we can draw thousands and thousands of different samples from the same population just for the sake of seeing what they look like. And I've plotted all of these on the same scale so that they're directly comparable. So you can see that the values are much more spread in the small samples compared to the larger samples where they are narrowly condensed around the true value of the parameter. Almost all means of samples of size 1000 are very, very close to the parameter value of 0. This is not the case for the means of samples with size 10. And the means of samples with size 100 is intermediate. What we're interested in here now is the shape of these distributions. So what is the shape of the envelope of these histograms? Well, as these are just sets of numbers, we can calculate their means and standard deviations. So for this set of numbers, which are means of samples, this is a sampling distribution, we can calculate their mean, the mean of all these, and their standard deviation. So the mean of means of samples of size 10 and the standard deviation of means of samples of size 10. And here, the mean of these means and the standard deviation of these means. And for each set of mean and standard deviation, there is a corresponding normal distribution curve. So I'm going to plot the matching normal distribution curve, that is, the normal distribution curve with mu and sigma equal to the mean and standard deviation of each of these histograms. Here it is. Does it look like a good match to the histograms? Yes, it does. So what this says is that the sampling distributions of means of samples drawn from a normally distributed population is approximately normal. Again, don't forget, these are distributions of means here. They're not distributions of samples. We're not saying that if you sample randomly from a normally distributed population, you'll get an approximately normally distributed sample. This is true, but that's not what we're looking at now. Now we're looking at the distribution of means from lots and lots and lots of different samples. And we're saying that the means themselves are normally distributed. What if the population wasn't normally distributed? Let's look at another population. This is really not normally distributed. This is the normal curve. And these are data actually uniformly spread over the range. So this is a uniform distribution. Let's sample samples of different sizes from this one. So 10,000 samples of size 10, 10,000 samples of size 100, 10,000 samples of size 1,000. For each sample, get the mean and standard deviation, and then plot the histograms of those means and those standard deviations. This is what we get. Again, we see that the means and standard deviations are more spread for the smaller samples. So it's more likely to get estimates that are farther from the population parameter with small samples than with really large samples. But what we're really interested in, again, is the shape. Let us plot the normal curves on top of these histograms. It's a pretty good match again, although the population was certainly not normally distributed. Let's try a different population distribution. How about this skewed one? This is not a very good match to the normal distribution because of the right skew. Let's do the trick with 10,000 samples from each of the three sizes, 10, 100, and 1,000. Here are the sampling distributions for means on the top and standard deviations on the bottom. I did not confuse the slides with the previous ones. These are actually the new values. If I plot the normal distributions on top, we see that these are again approximately normally distributed. Well, less so for the smaller samples and less so for the standard deviation, but still. Look at this one. How about a really skewed, a horrible non-normal distribution? Let's sample from this one. What are the sampling distributions for the means and standard deviations now? Okay, now they're a little worse than before. Let us plot the normal curves on top of them. We see that for the small samples, the approximation is not very good. And for the standard deviation, it's not that good. But for the means, it's better and better, even from such a horribly skewed distribution in the population. So it's the means that we're actually going to concentrate on because it's the means that are usually interested in making inferences about. And what the central limit theorem says that is important for us is that the means of independent random samples are approximately normally distributed even if the population is not normally distributed. So the population may not be normally distributed, which means that the samples from the population will not be normally distributed, but the means of the samples will be approximately normally distributed as long as the samples are sufficiently large. And this greater than 30 is a number that you may see frequently in the literature. 30 is really kind of an absolute minimum. And as you saw, it doesn't work very well for a really skewed distribution. So you shouldn't think of 30 as sufficient. You should think of 30 as just the bare minimum, and you should always try for something much larger, especially if you're not sure about the distribution in the population. Now, why do we care about the distribution of means of random samples? We care about this because the sampling distributions are what could have happened if we'd picked another sample. So if we know that the means are normally distributed, although of course we don't know what all the other values would be, well, we can still link standard deviations to probabilities through the known link via the normal distribution. 68% within one standard deviation, 95% within two standard deviations, and all that. So if we can imagine a distribution of means with a standard deviation, then we can figure out the probability that the mean lies within any given range. So the central limit theorem that tells us that the means of all the samples, those that we haven't measured, we only have one, but the means of all the possible samples are going to be approximately normally distributed, which means that we can apply the link from standard deviations to probabilities. It allows us to figure out the range of findings that are associated with a given confidence. In other words, how likely are we to be a certain distance from the true value, and how confident we can be that our result is within some distance of the population parameter.